This is question number 50 from the Halliday, Resnick, and Walker book. The question reads, the current through the battery and the resistors 1 and 2 in this figure is 2 amps. Energy is transferred from current to thermal energy in both resistors. Curves 1 and 2 in the figure give the thermal energy for resistors 1 and 2 respectively as a function of time. The vertical scale is set by E thermal, S is equal to 40 millijoules, and the horizontal scale is set by 5 seconds. What is the power of the battery? So let's first take a look at the schematic. We have conventional current flow leaving the battery here and flowing through resistors R1 and R2. Of course, the same 2 amps is flowing through both of those resistors. We don't know their values, but we're asked about the power of the battery. And so as the resistor restricts flow, energy is transferred out of the system as thermal energy. And this graph here that we're given of thermal energy with respect to time, is something you guys should pay attention to. And the reason is we know that power is the rate at which work is done, and work is equivalent to energy or changes in energy. So, when I look at this graph and I understand that the derivative of the energy function is power, I can see that I just need to find the derivative, in this case, the slope of the line. Using the scales for curve 1, the slope of the line, or power being the derivative of energy, would just be 16 over 4 seconds. I take that back. It's not going to be 16. The scale is set by 40 millijoules, so each one of the small lines on that graph is 4 millijoules. So therefore, the height of the change in y is going to be 32 millijoules, and the time is going to be 4 seconds. And so therefore, we can see that the power is going to be 32 divided by 4 millijoules per second, or milliwatts. So we're going to get 8 milliwatts is going to be the power dissipated thermally out of resistor number 1. And we can kind of do that again if that's resistor number 1. Resistor number 2 would be also dE over dt, but it's going to be a smaller value. In this case, it's going to be half of that. It's 4 lines up. Each line is 4 millijoules, so it's going to be 16 millijoules over 4 seconds, which is going to give us 4 milliwatts. So we have the power dissipated by both resistors R1 and R2. They're 8 milliwatts and 4 milliwatts, and so therefore the power delivered by the battery is going to be the sum of the power dissipated by the resistors. This is a B subscript here, and so we get 12 milliwatts as our answer.